in psychology, especially he helped to develop a lot of statistics for SFT. So actually, I know Joe at the Sacramento conference. So I went to Joe's poster, and we chatted a lot about how to apply SFT. So even now, I and my students and my colleagues learn a lot from Joe's, and we seek for Joe's help to help us to do analysis. So today, Joe is talking about the application of SFT. So please join me to welcome Professor Joe.
Well, thank you very much. And I don't think I can be so eloquent in saying so, but as Ami was, but I deeply appreciate all the effort it took to put this together, the honor of the invitation, and the opportunity to hear from both my colleagues from all over the world and the graduate students here. Such amazing research. So I'm very excited to talk about this work that I've been doing to continue further development of systems factorial technology. I apologize if it's kind of heavy on the technical side, but do feel free to interrupt me at any point. I'm happy to go into more detail. I've got the talk kind of modular, so if we go into more depth with a particular topic within the slides, it's no trouble. I can skip over a section and we can talk about it over coffee later and generate more great research. Good to go? Okay. So, nope. Apologies for the extra trouble. There's kind of some neat 3D graphics that I've included that it's just easier to run from the laptop. It's a minor point, so I apologize for making all this additional difficulty for the minor point. But I'll spend a lot of time with flashy 3D graphics just to really make it worthwhile. Okay, so the core driving factor of what I've been doing with this research is, number one, that systems factorial technology is an incredibly powerful tool. It's something that as soon as I learned about it after joining Professor Townsend's lab, it amazed me that it wasn't used everywhere. It answered some of these core questions that come up over and over, particularly in perception and cognition, but as we've seen with Ami's talk, shows up in more social psychology type situations as well. And I think there are a number of applications of this technology even beyond psychology. And so in my graduate work, one of the things I thought was a potential concern for the application was that people were concerned about the qualitative evaluation of SICs and capacity coefficients. And so I made it my goal to develop inferential statistics to go with it. In this work, one of the things that I've identified as a potential reason for not wider uptake is one, the limited treatment of errors in the original systems factorial technology. If you were able to attend the talks yesterday, we saw some of the updates that Jim talked about to include errors, but also extending even more broadly to multiple choice situations. So rather than a correct or incorrect response, maybe you've got 3 different choices or more, and how SFT can apply that. So that's the kind of goal, continue to extend this incredible theoretical framework in a way that it can apply even more broadly. I'll go fairly quickly through this because hopefully this is repetitive content at this point, but just to make sure we've got the foundation. The systems factorial technology is all about how people or systems combine multiple sources of information for a decision. And that multiple sources of information can be pretty flexibly defined. So in the original Townsend-Izawa paper, it was just 2 dots on the screen. This is an example of a follow-up to that study and not actual stimuli from it in the top left. but it could also be multimodal stimuli, lights and sounds. It can be things that we might not even necessarily think of as distinct sources of information, like the top and bottom half of the face. And it also has clear technological application. So the bottom right is some work we did looking at multispectral fusion. If you've got a thermal sensor and a visible sensor, what's the best way to display it? SFT, it turns out to be an ideal framework for answering those kinds of questions. And so one of the strengths of this formality is it takes this broad question of how do we combine multiple sources of information and breaks it into more tangible sub-questions to cover the different aspects of that broader question. One, whether we use the multiple sources of information sequentially or concurrently. Two, how much information or how many of these sources are enough to execute a response. Three, what is the influence of one source of information on the other? Or how are they related to each other during the processing? And then finally, how things change as we add more and more things or sources of information to deal with. So in the SFT parlance, architecture is the kind of framing we use for this question of how the temporal structure of processing happens, whether things happen in parallel as in this diagram or serial as in this diagram, or the special case of coactive that we've heard a lot about. Likewise, this question of how many sources are enough to respond, we refer to as stopping rule. Often, particularly in these simple cases, it just maps onto a logical gate. So at exhaustive processing, we need to wait for all sources. The first terminating, if any source is enough, or self-terminating, that there's some kind of stage at which the process can stop. This not necessarily the exhaustion. Often in the theory, the interaction between sources is described particularly in terms of stochastic dependence. So the statistical, the probabilistic relationship among the processing times of each of the sources. And we've explored more process-oriented ways that might lead to different types of interactions here in the work. And then this final question of how processing changes as we add more sources, the question of workload capacity in SFT terms. And this is usually assessed both quantitatively, but also qualitatively in the sense that limited capacity is a situation where whatever resources I have to dedicate to the processing source of information are reduced when I have more sources of information. Unlimited capacity, if there's no change as I add more sources of information. Or supercapacity, if I'm able to dedicate more or become more efficient with more sources of information possibly. So again, just at the high level, the goal of SFT is to answer these broad questions of how multiple sources of information are combined to come to a response. Usually we think of those in terms of cognitive processes, but it could be social processes or other types of information. Question of architecture, what's the temporal ordering, or how are different sources used concurrently or sequentially? The question of stopping rule, how many information sources are enough to respond? The question of workload capacity, how the resources available change as a function of how many sources we need to process, and dependence, the interaction between the different sources over the course of processing. All right, so that's background on SFT. Again, hopefully a refresher to many people in the room, and again, something you heard about yesterday a couple of times. The next piece of background information that's going to be valuable for the remainder of the talk are choice accumulator models. The two, I would say, most commonly used of these are on the left side, the LBA model, on the right side, the drift diffusion model or decision PDM. The basic idea here is that it's a model of how we gain information over time towards a choice. So, for example, in the LBA model, there's some start point of how likely I am, how much information I might start with for a particular decision. And then over the course of time, I linearly increase the amount of information I have, the amount of preference I have, until I reach a threshold of that particular choice. And often this is framed with multiple choices as separate accumulators for each of the choices. So I may be deciding whether I want to have coffee or tea. My coffee accumulator starts higher and increases a little faster, but sometimes I happen to increase more quickly in preference for tea, and that reaches the threshold first. The DDM variation of that is that there's accumulation over time, but rather than increasing linearly, there's a stochastic process that unfolds. And it can either be a single process leading to one or two bounds, or you can run multiple of these processes. Usually the standard is just a two-decision model where there's a single process that gets one of two bounds. And these are just two examples of trajectories in that. So these types of models have been really impactful in cognitive science, particularly in mathematical psychology, as a way of translating from choice and response time data to more interpretable or theoretically meaningful parameters. The downside of those models is that they make fairly strong parametric assumptions. One of the strengths of systems factorial technology is that it avoids making strong parametric assumptions. So we stick to distribution-free estimates or non-parametric estimates, and avoid these kind of very particular structural assumptions about what's going on underneath the hood. That brings up a third model that is the GRICE that I referred to in the title of the talk. It was proposed, I believe, in the 50s, where rather than having a variable accumulation process of information, the model assumes that there's a deterministic accumulation process. So across trials or across contexts, the way I accumulate information is exactly the same. But the variability that we see in choices and response times comes instead from a variable threshold. So how much information is enough? How much sort of accumulated preference for coffee is enough for me to say, I'm going with coffee today, is the thing that varies across day to day or hour to hour, depending on how many caffeinated beverages I'm having. Does that basic model make sense to everybody? And then the way we go from a single choice option to multiple choice option is we just have additional accumulators. So maybe my tea preference indicator doesn't quite rise as fast. And then I would separately have a threshold that I randomly choose for coffee on that particular day and for tea on that particular day. And so this offers the flexibility of adding more and more choices fairly easily. The reason I particularly like this model is, one, its simplicity, but two, its universality. So in some cases, you might think of universality of a model as being a weakness. It can be disproven. But from my perspective, the universality of this model means that if I choose to use it underneath the hood and showing things about systems factorial technology, I'm not actually making any constraining assumptions. So universality in the sense that if there's any distribution of choice and response times, there's a GRICE model that can represent that process. So it's equal in distribution to that process. Furthermore, it has the advantage that if I choose for the random threshold process, an exponential random variable with rate parameter 1, that these accumulator things just become the cumulative hazard function. So for those of you that are familiar with the math of systems factorial technology, the cumulative hazard functions show up quite a bit, and Jim again introduced them yesterday in talking about capacity analyses. So not just is it universal and not making stronger assumptions, but it actually just ties in quite neatly to a way of representing random response times that's already well integrated into systems factorial technology. As an aside, one of the things that I also like about the universality of these GRICE processes is that you can then use a GRICE representation of a model as a way of translating a sort of Rosetta Stone across modeling frameworks. So in the same way that Ami and Jim had worked on taking different bounds in capacity space, mapping them into a single space as a way of seeing the relationship between them, we can take a Grice representation of an LBA model, a Grice representation of a DDM, even a Grice representation of something more disparate like ActR, and map it into the same space to be able to then see what the different relationships across the models are, how parameters change things in that Grice space and relate to each other. When I get to the last section of the talk in coactive models, these other aspects of the space are going to be useful as well. So in particular, not just that I take, say, a particular LBA model with particular parameters and figure out what the right cumulative hazard functions for each choices are, but also if I look at two different sets of cumulative hazard functions, questions of how far away apart they are, gives us some properties of that space that end up making it convenient to do things like essentially derivatives. And I'll highlight when I get there the value of that. So it's useful to talk about in this space then what we think of as distance. And there's not just a unique distance that makes sense for it. For the slides later, I'll focus on L2 norm. I'll explain that later. But there are other reasonable distances for this as well. There's a variety of statistical distances. Earth movement distance, if you've taken classes in computer science, that's a favorite one there. You can even inherit essentially a distance metric from one of the models for the subset of space where that model works. So how much I change drift rate as a metric for how much we change in the space.
Joe?
Yeah.
So will this also take into account, like in a sense, something dear to our hearts, of selective influence in the sense of two models might occupy very predicted space, but one has almost, say, for a particular point, has almost never all the weight on the drift parameter, for example, and another one has almost all the weight on the bounds, decision bounds, and that might be extremely important in the distance in some sense.
Absolutely. Yes, and it makes me doubly glad then that I have my nice 3D pictures, because I'll kind of get at the parametric idea of selective influence in those figures. Sorry, time to look at a picture. I need to change the share. Good angle to start with. Okay, so this is kind of a mock representation of the LBA model in Grice space, where each of these lines is going to be a single set of a particular combination of parameters for the LBA model. This is just for let's see, this is a two-choice model, so there's a correct and an incorrect accumulator. And so I can look at it from this projection. This is going to be the incorrect accumulators across time. Or I can look at it from this projection, and this is going to be the correct accumulators or cumulative hazard functions across time. And so I'll show a figure later, Jim, that's more directly answering that. But one of the things we can ask then is, what is the subspace that's carved out by only changing a particular parameter? And so if I have an experimental factor that only influences drift rate, for example, I should expect to only find cumulative hazard functions along a particular subspace there. If I'm not selectively influencing that parameter, then I might see more of a spread around. So again, this kind of cloud of points, and then this is a subset just because the dense cloud doesn't make for a very pretty picture. This cloud of points can be thought of as LBA in the Grice space. So this is the range of possible predictions that an LBA model can make. For the most part, there's not a lot of direct insight to see from this. So I can get a good spin on this. One thing you'll note is that there seems to be this diagonal boundary here that it's not crossing. This is because I assumed that the correct accumulator was always going to be at least as high as the incorrect accumulator. So that then puts this bound on the space that we're only seeing cumulative hazard functions in this range. So again, if we wanted to, then we could also have like the cloud of the DDM and look at the regions where they overlap or not, the cloud of ACT-R and look at the regions where they overlap or not, and that might suggest experimental designs. The next kind of piece of background information that's going to be valuable is a tool from survival analysis. So again, survival analysis was introduced a couple of times yesterday. This is an area of statistics that was originally interested in actuarial things, whether it's how long is a person going to live, or how long is a particular light bulb that I've screwed in going to last before it stops. And one of the things that comes up in survival analysis is this idea of a censoring process. So a censoring process is something that happens where all I know about the event is that it happened after a given time. So I know right now that all the light bulbs in this room worked, but as soon as I leave the room, I have no idea how much longer they're going to work. So I can either just throw that out and ignore it, but that's actually going to then bias my estimates of the lifetime of these light bulbs quite a bit, because I'm throwing out all the long-lasting ones from my data points. So instead, I need to have a model that accounts for the fact that something takes longer than a given point. So I want to use exactly that amount of information. It's just longer than my cutoff point. Right, or if this is a I don't want to get too morbid and actually talk about births and deaths. Does the idea of censoring make sense, though? So this is something that shows up a lot in statistics. In terms of response times, we often have in our experiments a cutoff for when you have to respond by. So if somebody hasn't responded within the first 2.5 seconds, something flashes up that says you're too slow and then moves on to the next one. Note that if I have a long tail in my distribution, like response times tend to do, I'm probably actually cutting off some of that tail and biasing my estimates a little bit faster. What's even more valuable, on this? Okay. I'll transition to that point out of the way. Okay, so moving to the statistics or the estimation of price models, we're interested in a cumulative hazard function, estimating that from data, but we want to do so in a way that can account for censoring. First, just for censoring things like you cut off the response times in 2.5 seconds, but also because when you have a race model, so in the Grice design, each of those accumulators are just racing against each other. When the other one wins, that is a censoring event for the first one. So in particular, within the Grice model, my estimates of the cumulative hazard function correct is I can treat any incorrect response time as a censoring event at that time. And so that allows me actually to get a more representative estimation of correct response times. And then likewise, looking the other way, anytime I have an observed correct response, that's censoring when I would have observed the time that the incorrect racer would have eventually hit its threshold. And so this Nelson-Olin estimator has already been worked out long ago for getting a statistical estimate of that cumulative hazard function. This is something that we've already presented in the statistics for cumulative capacity coefficients. We use these estimators underneath that. So that CZ statistic that you saw show up a couple times yesterday is based on this Nelson-Olin estimator. Okay. So that's all the background information. Now I'm going to dive into two particular applications of this Grice model within systems factorial technology. The first one being workload capacity. So again, the idea of the capacity coefficient is to assess the performance, cost, and benefits as we increase or change the number of sources of information available. What we need is a measure that's robust against changes in speed, accuracy, trade-offs. And so Jim talked about the assessment functions yesterday. That's one of the approaches to addressing that. And again, we need to account for changes in choice probability speed. And the goal then of this work is extending to more than just the two options as So again, quickly, just the existing measures in this domain, the capacity coefficient, which again you saw a few times yesterday, where we look at the cumulative hazard function for multiple sources together, and compare it to a model-based prediction estimated from each source individually. And then that relative difference from the model-based prediction gives you a metric for capacity or change in information efficiency. And so we see graphs like this, where if it's unlimited, there's no change. When we add more sources, we see something around 1 for the ratio. If you get a bonus of having more sources of information, you see lines above 1. Or if there's a cost of adding more sources of information, you see lines below 1. Major detriment of this approach is that it can't account for speed accuracy trade-offs. So in the original analyses, we sort of assumed that we were working with very high accuracy data, and that the sort of throwing out those incorrect response time wasn't going to bias it too much. Oftentimes, though, in cognitive psychology or any application of SFT, we do have a higher rate of other choices. So the first solution proposed to this problem was to take a parametric modeling approach and take the LBA model, which again can include multiple outcomes in the process racing against each other, and then parametrically fit the models to each source individually, use those parametric fittings to predict what the model should be doing under that baseline assessment, and then see if things are different. So rather than seeing these capacity functions across time for our assessment metric, this particular paper proposed basically the change in drift rate relative to what it should be if it's using this baseline model to what you've actually observed. So limited capacity would be there's a relative decrease in drift rate, relative equality in the drift rate, a relative increase in the drift rate. So this is strong, and although the paper didn't initially look at multiple responses, this does extend pretty easily to more than one response. That's one of the strengths of LBA, is it's very flexible in that way. The downside in terms of the SFT collection of tests is that it does make pretty strong parametric assumptions. So we have to be comfortable with using the LBA model as our choice of information processing mechanism for this to be a meaningful metric. The next approach are the collection of assessment functions that Jim and Nick Altieri proposed. So these are non-parametric. I put this up as a downside, but if I were going to include all the equations of the new work, it would look even worse than this. So I could say it's a downside that the equations are long and don't fit on a single page, but I didn't really fix that problem. But we have separate assessment functions depending on experimental design. There's kind of a trade-off between speed and accuracy in the analysis here. Switching to a little bit more interpretable way of looking at these things are just predictions under model simulated data. And this is to highlight one of the things to be aware of with assessment functions is that the way some of the assessment functions are set up is that it picks a particular weighting of accuracy and response time. Wherein if you use, for example, first of all, if you use the correct and fast response time, higher accuracy gives you better numbers and faster response time gives you better numbers. So both of those factors are pushing in the same direction, and you see kind of the same order you expect. No change based across baseline, we see unlimited advantage across baseline, we see a big bump up, disadvantage goes down. For the incorrect and slow, it's the same thing but in the opposite direction. So more incorrect and faster pushes you up. So we want to see for the incorrect and slow, kind of the worst models be higher, better models be lower. What's interesting though for the correct and slow is incorrect and fast, is that the models pick a particular trade-off wherein you can see even switching it across time, in this case with these very specific parametric assumptions, where you might actually see for early times an advantage for one model, but then later a disadvantage as that trade-off between the shape of the cumulative hazard function and the accuracy unfolds over time. So there's additional complexity in having 4 different functions for assessment that come in with this, and so one of the goals is to try and come up with a single metric that accounts for all of the response time and accuracy trade-off. Right, and then the other piece is that those equations are rough to work with, and we don't really have a good go-to statistic. So bootstrapping is a nice default, and that's often the go-to for looking at differences in assessment functions. But there's not the same kind of inferential statistic like we have for the capacity coefficient. All right, so the proposed solution for this case then is to take this same insight from the assessment functions and the capacity coefficient of taking a baseline model prediction and then looking at deviations from that baseline model prediction as a way of scoring how well we're doing with more sources of information. And so to do that, we take this idea of the USET model as the baseline one I've been referring to, and we project it into the gray space. So as I assess how well you do with one source alone, I'm going to use that to predict in the gray space what I would see for those cumulative hazard functions that represent the individual racers. So this would be, maybe this is an audio-visual integration task. I might have my correct and incorrect cumulative audio, correct and incorrect for visual, and then I would want to take the model-based prediction of how we would combine these. So for some cases that's easy. If you have a discrimination task with a first terminating stopping rule, you can just get the model-based prediction for the correct accumulator is just the sum of the two correct. The model-based incorrect is the sum of the incorrect. I handpicked that one to not look too ugly. This is just the start of what you get with a detection task. I think in the original presentation, this had 6 slides to go through all of it. So again, things don't get simpler in terms of presentation. But what it does do for us then is we get these kind of changes, and I don't have the 3D graphic loaded for this one, but I've shown just a couple projections where I have this kind of USET baseline here, and then simulated models where I have an advantage of more sources or disadvantage of more sources, or no change of more sources. And so I can look across the correct cumulative hazard function. We see projection where I have this kind of USET baseline here, and then simulated models where I have an advantage of more sources or disadvantage of more sources, or no change of more sources. And so I can look across the correct cumulative hazard function. We see that ordering we expect to get higher values of that correct cumulative hazard function for more advantage, lower values for disadvantage. On the incorrect one with this particular simulation, but it would be model dependent, we actually don't see much of a difference across the incorrect processes. But the idea here is, in this space now, I've got my baseline, and I can look at deviations from that baseline to get my assessment how things are changing. Yeah, Jim.
So, what assumptions do you make about the decision bounds as you increase the drift rate or whatever?
It's so that's where we get the different task specific. Just like in the assessment function, we've got to have a discrimination and a detection or and so on and so forth. The same kind of thing shows up here, where if you have, in this case, a first terminating discrimination task, that means as soon as I've detected one as targeted, or determined that this is a high auditory tone, I can say, we're good, it's high auditory, I'm going to respond. So I don't need to wait for the visual, nor any of the low auditory, low visual things. But to do detection, you end up with more complexity, and you accidentally thought it was high when it was low on the auditory, and you have to account for that in the same way that the assessment functions have to account for that. Okay. I guess the ugly side to this, so like I mentioned before, there are different ways of putting metrics in this space. Better and down here is worse. But exactly how I turn this into a single number, or even take all of the information from this 3D space that goes to even higher dimensional space, and I have more choices, and project it onto something I can put in paper reasonably. And that does require more specific assumptions. So essentially I have to pick a way of representing that trade-off. One way of picking that actually leads to the assessment functions. So this can be in some ways thought of as a generalization of an assessment function where you can make a particular choice about speed accuracy trade-off and end up with, again, with this one would essentially be the correct and fast one. In this case, I just, for demonstration purposes, just took a sum of the two dimensions. So the correct accumulator, I guess, minus the incorrect accumulator, minus the linear combination. I don't remember exactly the linear combination. Just to highlight a downside of that, when I project onto one dimension, if I just use the correct accumulator, things work just fine. But the incorrect accumulator, in these data, there weren't a lot of incorrect response times, simulations. So there's a lot of uncertainty in that. And so then when I have them up to get my single measure of capacity, I inherit all the noise of that uncertainty in the measure. So there may be, I mean, you can just weight them according to the number of response times, but there's a lot more choices that go into trying to cram things into a single number of dimensions. I'm going to jump now to the co-activation question. Hopefully not keep you too much longer. So coactive models, again, they've shown up a couple times, especially in talks yesterday. They're of particular interest in some subsets of cognitive psychology. They show up in our interest around configural perception. There's a lot of discussion of coactive models in terms of multimodal integration. So I'd say, even though it's one of the five, or even a special case of a more general parallel model within the SFT framework, it is due special attention in terms of its application. Just to kind of highlight a contrast with some of the approaches, what we look for in assessing coactivity in a model is to have a theory-driven measure, not a measure-driven theory. In the sense that I don't want to define coactivity in terms of changes relative to some metric. Instead, I want to start with the definition of coactivity and derive what the right metric is. And again, within the SFT framework, we want to keep our assumptions minimal. Okay, so the coactive model, we'll call these Mariograms. The idea is that we take multiple sources of information and they're pooled before making a particular decision. So that's roughly the SFT interpretation of it. In some literature, there's an argument that anything that violates the race model equality should be called coactive. In other cases in the SFT literature, we've defined coactive processes in terms of more specific parametric processes, at least for analyzing things like SICs for coactive processing. And then a third definition that I'm going to highlight kind of at the very end here is to call it processes in which speed manipulations on each source are indistinguishable. In the sense that if I'm messing with my speed of A, it's all getting pulled for the decision with anything I'm going to mess with my speed for B. So once I do this addition, this summation process, I lose the distinguishability of my influence of A and my influence of B. And so that's kind of another view or another definition for coactivity in this case.
Right, Joe, just throw in there real quick, as people over decades did not notice that, and notice that you can't make logical decisions like or and stuff like that, so you lose all that wisdom.
Yep. Yeah, exactly. So once you've lost the two sources of information, there's just the only, my sort of total perceptual stuff going on in my head decision, rather than that I hear a tone or that I see a dot. Yeah, absolutely. The Miller-bound approach, I won't spend a lot of time on that. Just as a kind of highlight, an upcoming paper where mostly Jim, with some background support from me, has demonstrated much more general cases that you get the kind of standard collective SIC signatures with a much wider class of models than just the Wiener process or the Poisson process that we work with. So just to highlight for that, the other one, and this is coming back around to Jim's question earlier on about selective influence in the LBA space. I'm not going to spend a lot of time defining Javron selective influence, but check out the talk in Taipei about the rise of selective influence, because I think it's valuable in all sorts of ways, but particularly for the reason I talked about in defining the coactive model, that you lose that influence of separate parameters when you have coactivity. So this sort of complete falling apart of selective influence, or thought of another way, is each thing you manipulate are only influencing the same single thing, can be a way of thinking of coactivity. Okay, so to get just a little bit technical, I talked about, I'm going to stop referring back to my answer to the question and just go for it. So, for example, if I've got my manipulation that is influencing how fast I detect the auditory signal, so maybe I make it louder or quieter, that I can just think of in my stimulus space as, moving kind of along a clean line. Likewise, if I've got my brightness manipulation from my visual signal, make it brighter or dimmer, and that's in the stimulus space, I can set up a grid of stimulus sets. Our question then is what that actually looks like in terms of the response space. I didn't get the exact figure. I was trying to replicate the figure from the chart that Jim gave at the International Society of Psychophysics. But essentially, we're going to map these stimulus dimensions into some latent space. So the way I change auditory and the way I change visual probably have some weird curvature and relate to each other in some way. And then it's this stimulus space that's actually what's influencing my response dimensions. And so if I have selective influence, it may not be linear, it probably won't be, but I'm still going to have some representation of whatever I do to my brightness and whatever I do to my loudness dimension. But if there's not selective influence, if it's the complete other end of the spectrum, if it's coactivity, then even if I'm messing with things on 2 dimensions here, as I carve those out, it's just going to follow along 1 dimension here. After that summation process, my representation of general perceptual stuff going on in my head. So we can look at that in terms of the LBA model to kind of get a sense of what that looks like when we interpret response times in terms of the LBA space. So same kind of figure here. So again, same kind of setup with this graph. I've got my time axis, I've got my correct cumulative hazards and my correct racer in the Grice model, and then I've projected out the incorrect right now. So there's the cloud of all possible LBA spaces, but I can look at selective influence, parametric selective influence in this sense, by seeing what happens if I take a particular model and just change one parameter. So this blue plane or subspace here, if I guess it's plane, is what we get if we just change drift rate. And in a coactive model, so this is just a single LBA model, but in a coactive model, the idea would be as I change auditory and visual drift rates, it's only affecting that single process. And so I'm always landing on this plane. This orthogonal is just kind of for demonstration what happens if I only change threshold. So you get these things when you change a parameter of carving out a subset of the space. It's a kind of lower dimensional representation. And again, we can just kind of pretends that maybe another way of looking at coactivity is, does stuff sit on a subspace? So connecting it back to this parametric selective influence idea. All right, so one attempt at actually asking that question of is everything sitting on a plane failed miserably this morning as I was sitting there with Ami looking over my shoulder. So I can talk to you about that over lunch. Another way of looking at this is once we've defined distance metrics in that space, we can look at our version of an SIC. In this case, it's going to be the Grice IC, I guess, because it's that joint cumulative hazard function. But I can look at the double difference. So in particular, as I mess with the visual signal and as I mess with the auditory signal, what's the relationship between those changes? So we do this kind of Jacobian looking thing, or maybe, I don't know. But we're looking at changes in that Grice representation with respect to changes in my manipulation of auditory and manipulation of visual. And what I should see, and do see, is for a coactive model, that essentially when I change things around with the auditory parameter, it's doing the same thing as changing things around with the visual parameter. So I see this symmetry in coactive models between those changes. So these are sort of the relative rates of change, or the second order difference with different types of changes. So if I change the visual only channel in two different ways, like the acceleration, I guess, of Grice, or if I change correct and incorrect, so those have no relationship to each other. This is an LBA model, so they're independent racers, so that's no surprise, and so on and so forth. But just to be sure that this is actually distinctive to coactive models, we can also look at things like a parallel OR model, and we see a big difference here now. So the change I'm seeing when I mess around with auditory is different than this interaction between auditory and visual, which is almost zero here. This, by the way, might also be an interesting thing to explore. We get sort of a zero Grice IC for parallel OR for this particular case. So that might generalize, might be related to some stuff that Bob has done, and maybe some of the other stuff out there. And then likewise with serial OR, we see different numbers across those two. Just to sort of do the same thing visually, so if we look at a lot of different simulations, we always get the same thing for that sort of Grice IC. So this would be that change in change in Grice with respect to audio-visual, or visual-auditory. I'm sorry, visual-visual, visual-auditory. It's always the same. Serial OR, we end up all over the place. Parallel OR is always zero. And just to wrap up then, so right. So with this coactive aspect of the talk, the goal is to take this broader Grice representation framework, which I kind of highlighted some advantage of early on in the talk, and look at this question of coactivity through that lens. And in particular, we're looking at how our stimulus changes influence changes in that representation space, which has some similarity in information geometry. That kind of magnitude of second partials is a big piece of information geometry. But it also connects to ideas of selective influence in processes as well. All right, so in the ultimate conclusion then, this Grice representation approach can give us a lot of opportunities to extend SFT into new potential applications. And we do so without compromising this non-parametric nature. So we're not making specific parametric assumptions. All the statistics that we build in are non-parametric statistics. We never assumed a distribution or anything other than simulations here. This includes accuracy and choice and extends to multiple choice. So I've shown for ease of use just 2 accumulators. I can have as many accumulators that have choices in these things. So we've looked at this sort of progression from capacity coefficients to assessment functions to these generalized assessment functions, to a deep dive on coactive architectures, and then again, kind of coming off of this, Grice interaction contrast seeming to have a zero signature for parallel, or perhaps there's more that can be done with parallel and serial architectures. I note Lapin here just because I'm not sure if it got published, but I know he was talking about cumulative hazard functions as a way of identifying parallel architectures as well. But then also the work that Dan Little and Jim and others did looking at error response times. Matthias Gondon's done some stuff with censoring these processes. So trying to kind of collect all of that work and build on it as well. All right, thank you very much for your attention for all that. I know it was a heavy technical talk, but I really appreciate your attention, of course.
I'm going to definitely ask you a question.
Great.
Yeah, it's really fascinating work. I just finally started to read the Ashby and Bamber take and much more general and theoretically astute treatment of state trace
Yep.
analysis. And I'm very curious as to whether that might have some relationship to your work. And your work is so general, I'm almost wondering that if there might not be a subcase of yours at least taken off at a topological level, or maybe yours is a subcase of part of yours is a subcase and there's not overlapping or something like that, but it strikes me as extremely interesting because, of course, that work is also non-parametric and very general in nature.
Absolutely. No, I think there's, well, yeah, first I think that's a fascinating idea. I think it would be really exciting to look at the relationship between that generalized state space and selective influence broadly, in particular, how it relates to this idea of coactivity here, projection of dimension. I think the major distinctions would be the dimensionality of their data. So I'm looking at the full functions of data. They're looking at particular sort of univariate outcomes in that, or just countable. I think it generalizes pretty easily to countable outcomes. Whereas the cumulative hazard function in theory is a continuous function.
Sure, like in function space or something.
Yeah. So I don't know that that's consequential, but it's something to be aware of. The other one is that I think they don't make a strong assumption, so they don't really need to say anything about how big steps are in space. They don't need a distance metric for the space. They just need that there is a jump as you go to one level to the other factors. And so that makes the experiment hopefully simpler, but then doesn't, it makes it a more general tool for the cases where it does apply, because it's just those ones. Kind of in the same way with the SICs, I just need that it's high and low. I need that ordering, but I don't need to know how much higher. Whereas in this approach, we need more of a sense of how much I change in that response time space as a function of how much I change the signal.
Right, yeah. One just, apparent overlap was where your coactive models, in their sense, would occupy a manifold of lesser dimension.
Yep.
That could be very one contact.
Mm-hmm. Absolutely, yeah. I absolutely agree. I think it's very exciting to pursue. Mm-hmm. All right.
So, I assume you need closed form for the models, to create cumulative hazard functions with the form of price representation. I'm curious, what is a closed form, for the serial process in
The assessment? Or
the model, the ground model,
yeah, so it's, yeah, the LBA. So the
cannot really, I don't know how you can present those forms for this model, how you can then make a price representation like that.
that one,
Is this something like hack or?
yeah, that one was probably simulated. Some of the stuff, the Grice representation is a lot easier for the models. So like with the LBA model, the Grice representation, I only care about my correct cumulative hazard function separately from my incorrect one. And so because I can estimate those separately, it vastly simplifies what I would need to do to sort of account for the fact that it's correct and it's beat incorrect. So in the Grice representation, I don't care that the H sub C that I have there is not a cumulative hazard function conditioned on actually being correct. It's my correct racer. And so that allows me to just take a single LBA, a single choice LBA model to represent the HC. Now, when it's a serial exhaustive model, I still have to deal with the convolution. And it's not that that's a trivial density to then convolve with itself, but simple enough numerically to deal with.
Joe, could you remind me how does the grass representation explain this?
So in the 3D plots that I have, these are actually a single line. So the Grice representation is a mapping from time to positive real numbers and whatever dimensionality of the choices you have. So this thing would actually just be one curve in that 3D plot. But if I project it down on just the correct and just the incorrect, that's what it looks like here. And so speed accuracy trade-off here is going to be represented by more accurate is shifting both functions, faster is shifting both of these this way. Because the more you shift them this way or push them up earlier, the more likely you are to hit the threshold earlier. And then accuracy by time is what the relative height of these things are. So this model is going to predict if your late response time are going to be mostly correct. If your early response times are going to be closer to chance. So a speed accuracy trade-off essentially would be you shift both of them earlier, but then you squeeze the blue one in closer to the red one. Flip back to the cloud. Yeah, so what that would look like here is, my cumulative hazard function for correct would go higher, but also incorrect. And so if I look at it in this kind of side measure, my correct and incorrect are going to kind of hit closer to the same value. So I'm going to squeeze closer to this kind of axis that will be sitting out here.
Yeah, no, somebody else got a question. Oh, she was talking about this. One fascinating thing, I've been looking at what classes of models actually do predict. I mean, it seems like everybody takes it on some authority from God or something that when you expand your decision bounds, you always get slower and more correct. And I haven't seen that many cases where that's actually proved analytically.
Mm-hmm.
So people kind of assume it for everything. And of course, this originally came out with work by Stone and I guess who's some of the other guys, Walls and so forth, because they have, like, based on every sample is a sample of a likelihood function. Right? And there it's easy to prove that. Always is more correct and longer. But I don't know if that's true for everything. And it's even, maybe it's true, but I've proved it now for certain subclasses of parallel models.
Mm-hmm.
That obey certain, there's still are restrictions even there.
Mm-hmm.
They look like they're probably mid a lot. But and I haven't done a counterexample yet, but it looks like by weakening these conditions that you might produce things that don't necessarily get more correct as you expand the boundaries. So I think it's kind of interesting question.
Yeah, absolutely. And so I cannot picture what that's going to look like in gray space. Being a universal model, I know it can do it. But how that actually plays out and then how that maps into something like how that hits areas of the space relative to the LBA cloud or DDM cloud, I think would be potentially helpful.
It's probably, I think you can probably prove it, like some of the work that we did on activation. You can probably prove it for the price or at least for the LBA model.
Yep. Yeah, I don't know. Definitely an interesting thought. All right.
So one of the interesting topics, important topics in this domain is model selection. So some researchers want to know which model is better, best, and they try to use different statistics to comparisons. could this be used, to answer some of these questions?
This is almost a planned question, because Mario saw my talk in Midwest College. There's a project we're working on now to look at how we can use this gray space for model fitting rather than a likelihood representation. One of the, so essentially your idea of model fit would be if you've got a model prediction, whether it's a single parameter or a cloud, how close is your data, or how close can you get to your data in gray space with your best model fit. And with the closeness, again, depending whether you choose L2 distance or root movie distance or something else. The advantage of gray space over traditional likelihood space is one, again, it simplifies the model estimation. So if I don't have to deal with, particularly with drift diffusion model, if I don't have to deal with competing, whether I hit this threshold first or that one, it's not first exit time, it's first passage time. That simplifies the math quite a bit. But with LBA, I just pick a single accumulator model. That's just one distribution I'm dealing with, not the distribution for every choice. So numerically, things become simpler. But I think even more valuably, that Nelson-Olin cumulative hazard function allows us to deal with censoring. So if I'm fitting my LBA model to data where I might have thrown away 5–10% of the data because it was too slow, that's going to potentially dramatically bias my drift rate parameters, and maybe it's going to mess with my threshold parameters relative to what the participant is actually doing. So if I'm fitting instead to a Grice representation, I've already accounted for censoring, I might get a better representation of how close I am to the model. So that's work in progress. The work I presented in Midwest College is actually, it didn't help any, but we're still working on it because I think theoretically it makes sense to do that.
Okay.
All right. Thank you all very much.
So we just end today's sessions. And by the way, we do prepare a this is for Timothy. This is for
Oh, thank you.
this is for thank you very much. And this is for Joe.
Excellent. Thank you.
那个一个一个合照。
We only did, shall we just go to the stage and take a few photos?
那个
I think we can have the certificates.